Hi guys, welcome to this video. This video is going to be a kind of update to a previous video that I've already made, and therefore we're going to be returning to a problem that I've already looked at in a previous video. The problem that we're going to be looking at is from the 6th term examination paper, or step 3 from 1987, and it's question 1 from that paper. So just to remind you what that question is, it's find the set of positive integers n for which n does not divide n-1 factorial. Justify your answer. Note that small values of n may require special consideration. Okay, so what's the purpose of this update video? Well, after having made the previous video where I presented my solution to that particular problem, I realized that there's a better way of solving the problem. So the solution that I presented in my previous version, and I will leave that video up and available for anybody to watch because I will actually make several references to it in this video as well. The solution that I present, as far as I can see, is still correct. It's just I had a bit of an idea that because of the fussiness and the messiness of the solution, that there was probably something better that could be done. And it turns out that that's the case. Okay, so I had a particular idea in my previous video, which I used as the basis really of my solution in that video to this particular problem. And it turns out that there was a better idea. In fact, it was another idea that I did use in that video that I failed to use to its full extent. Okay, I didn't realize how useful it could actually be. This is how it works with problem solving. And the reason that another reason why I'm going to leave that video up is because the whole point of the videos on problem solving that I present on this YouTube channel are deliberately intended to present the problem solving process in mathematics in an accurate light. Okay, to accurately reflect what that problem solving process might actually look like. So rather than the polished version of problem solving that you might see in the classroom or in your textbooks, for example, here I'm trying to capture the messiness. And part of the process, the problem solving process, is actually kind of critiquing your own work, reviewing your own work, and considering other possibilities, other solutions to the same problem. Just because you've solved a problem doesn't mean that you've learned everything that you need to learn from that problem. Okay, there's always little bits of extra juice that you can squeeze out of a problem. Obviously, there does come a point where it becomes like law of diminishing returns and things like that, where it's better really just to move on to something else maybe. But still, it's still worth considering, even when you've got a solution to a problem. Are there any other possibilities that kind of spring to mind? Is there anything else that you notice now that you've got the benefit of hindsight, knowing how to solve this problem in a kind of basic way? Is there anything that your mind is drawn to? Can you see things in a different light? So let's have a look at the problem then. So just to remind you again what the problem is, it's find the set of positive integers n for which n does not divide n-1 factorial. Justify your answer. Note that small values of n may require special consideration. So I'm going to be using a lot of the same ideas in this video as what I did in my previous video. So I'm not going to explain them all in detail because I explained them all in detail in my previous video, but I'm going to be using them in different ways. And there's a couple of ideas that I'm going to be using in a very different way. Okay, one of the main ideas that I'm going to be using in this video, as in the previous my previous solution, is the fundamental theorem of arithmetic. Okay, so the fundamental theorem of arithmetic means that I can write any number, any positive integer greater than or equal to 2 in a unique way as a product of prime numbers. Okay, and it might be powers of prime numbers. Okay, so we've got P1 alpha 1, P2 alpha 2, up to pk alpha k. As in my previous video where I used case analysis, I'm going to be using case analysis again here. So I am going to be making some restrictions on the value of n initially, and then looking at the values of n that I exclude in this case that I'm about to consider, I will consider separately. But it turns out that I can massively reduce both the number of cases that I consider and the amount of work that I've got to do actually show whether n divides n minus 1 factorial or not in each case. Okay, so there's a massive reduction in work as compared to my previous solution. Okay, so the restrictions that I'm going to make are, well, it's not a restriction, but pi are distinct primes, alpha I are integers greater than or equal to 1. So they're not really restrictions, but the restriction that I'm going to make is that k is an integer greater than or equal to 2. Okay, so that's definitely a restriction. So what this excludes is pure primes and powers of a single prime. Okay, so things like 17 would not be a case that I'm going to be considering here, nor would, for example, 81. 81 is a power of 3, right? Okay, so in this case, what I'm going to do is I'm going to let p alpha equal the maximum of pi alpha I. Okay, and there will be a maximum because there's only a finite number of primes here. There must be a maximum. So in that case, because there's at least 2, k is at least 2, there must be at least 2 primes involved here, so that means that n must be greater than p to the power of alpha. So that means that n minus 1 must be greater than or equal to p to the power of alpha, and therefore n minus 1 factorial is greater than or equal to p to the power of alpha factorial. So, as I've explained in my previous video as well, since this is the maximum over all of these values, that means that in the factorial, p to the power of alpha factorial, p1 alpha 1 will appear as a factor, p2 alpha 2 will appear as a factor, all the way up to pk alpha k will appear as a factor. In other words, all of these will appear as a factor in n minus 1 factorial. That's just properties of factorials, and therefore n will divide n minus 1 factorial. Okay. It's also worth noting, just for clarity as well, that because these are distinct primes, powers of distinct primes can never coincide with each other. Okay, so if I've got, for example, 5 to the power of x and 7 to the power of y, these could never be equal with integer powers. Okay, I mean, if we accept non-integer powers, then yes, they can be equal, but whenever we're restricted to integer powers, positive integer powers, x and y, these two could never be equal. These two expressions could never be numerically equal. Okay, so that's one case that we've considered. So now we need to consider, what about when we've just got a power of a single prime? Okay, so that's case 1. So what case 2? What if n is equal to pi to the power of alpha? In fact, so let's just say p1 alpha 1. Here we do need to start considering individual special cases. Okay, so n equals p1 alpha 1. Let's just have a look at if n is equal to just a pure prime. Okay, not a power, just a pure prime. So in other words, n is equal to p. Well, in that case, n minus 1 is equal to p minus 1, and therefore n minus 1 factorial is p minus 1 factorial. And as I've explained in my previous video, the same applies. Fundamental theorem of arithmetic will guarantee that p is not a composite number. It's because it's a prime number, and therefore p does not appear as a factor in p minus 1 factorial. So in that case, when n is a pure prime, and there's no restriction on the value of n here, n could be even equal to 2, 2, 3, 5, 7, whatever, n does not divide n minus 1 factorial. Okay, now we need to consider the case where we've got n is equal to p1 alpha 1, where alpha 1 is greater than or equal to 2. Okay, so we've already considered pure primes. Now we need to consider genuine powers of primes. And this is where we need to start looking at different cases. Okay, so on the one hand, we need to consider the case when alpha 1 is greater than or equal to 2 and p1 is greater than or equal to 3. And we also need to consider, as a separate case, when alpha 1 is greater than or equal to 3 and when p1 is equal to 2. Okay. Right. Okay. Oh, actually, in this case, we can include something else. Actually, we can include alpha 1. We can include this in here. P1 is equal to 2. So the same argument will actually work for both of these cases. No, so we can restrict this even further. We can just say a separate case when alpha 1 is equal to 2 and p1 is equal to 2. Okay, that's better. Right, we'll come to that later. So this accounts for both of these cases. Alpha 1 is greater than or equal to 2 and p1 is greater than or equal to 3, or alpha 1 is greater than or equal to 3 and p1 is equal to 2. The same argument will apply, because what I showed in the previous video was that if this holds for both of these conditions, in that case p1 alpha 1 will be greater than alpha 1 times p1. I'm not going to go through how that's proved. I proved it in my previous video. But in this case, this means that n minus 1 is greater than or equal to alpha 1 p1, and therefore n minus 1 factorial is greater than or equal to alpha 1 p1 factorial. And therefore, in this factorial, again, I showed it in my previous video, I can guarantee that there's going to be alpha 1 factors of p1. Okay, which means that n must divide n minus 1 factorial. Okay, so in that case, we get divisibility. And then the final case that I'm going to consider is the special case. And this, the hint that we're given, that, let me just read it out again. Small values of n may require special consideration. I think it's specifically referring to the case that I'm about to do, which is when, similar to this, when p1 equals 2 and alpha 1 equals 2. In other words, when n equals 4. Because I wasn't sure, and it's, when I first read this problem and I read the hint, and it's talking about these small values of n, I was thinking, does that mean n equals 2, 3, 4, 5, 6, up to some finite number? How do I know? And I just had to figure it out. Okay, sometimes you kind of ignore the hint a little bit, not always, but sometimes if it's not clear, you will get clarification further down the line, hopefully. And the clarification came at some point. I can't remember exactly how I managed to figure it out, but I eventually realized that when it's talking about the small values of n, it's talking about really this specific value. Okay, it's just something that eventually it pops out of the logic. Okay, these special considerations, these fine details. Sometimes when you've got a theorem stated, there'll be some really weird conditions included in the statements of the theorem, and you'll be thinking to yourself, what have they got to do with anything? And it's often just some technical point in the proof that requires those conditions to be in place. Otherwise, the logic just doesn't quite work. Okay, so the logic that I used here doesn't quite work in this particular case. Okay, so I couldn't extend this to this because I needed, for reasons that I explained in my previous video, I needed the strict inequality here between n and alpha 1 p1, which I wouldn't have in this case. I'd only have weak inequality. So I've got to consider this as a separate case. Okay, so that means that n minus 1 is equal to 3. So n minus 1 factorial is 3 factorial, which is equal to 6. Therefore, n does not divide n minus 1 factorial, since 4 does not divide 6. And that's it. Okay, this is my new solution to this particular problem. So there's fewer cases, and the working out is much less fussy. Okay, but still, a lot of the ideas that I've used here are ideas that I used in my previous solution as well. So if you've got any comments, anything that's unclear that you want clarification on, please leave a comment in the comments section. I'd love to help you. Please subscribe to this channel, by the way, and show your support. I'm really trying to do as many of these videos as I can to really help people develop their mathematics skills and particularly their problem-solving skills. If you're preparing for STEP exams, maths admissions test exams, advanced extension award exams, or if you're just doing your normal maths and further maths A-level exams, I want to help you prepare for those as best I can. I don't make any money from these videos. I do them for the hell of it because I enjoy doing them and because I want to help you. And I want to continue making these videos. So if you do want me to continue making these videos, please show your support by subscribing to this channel and hitting the like button and sharing these videos with anybody else that you think might find them interesting. So with that, I'm going to finish this video. Thanks very much for watching, guys.